Hello everyone, welcome back to LeetCode Daily Live, where I do the daily question raw and uncuts. So we actually have a hard today. It's called count number of balanced permutations. So let's read the question. Well, we are given a number, which is a string. How long can it be? It's actually pretty short. It's only up to 80 digits. And yeah, so it is like 0 to 9 only. So let's read the question. So a string of digits is called balance if the sum of the digits at even indices is equal to the sum of the digits at odd indices. So we want to return the number of distinct permutations of number that are balanced. So since the number can be very large, we want the modulo. Permutation is just a rearrangement of all the characters of a string. So I think like the length of 80 is kind of an awkward bound because it is way too big for an exponential algorithm, but at the same time it is extremely small for so even like n cube or like n to the power 4 kind of time complexity will work. But yeah, that's why it is a bit awkward. But let's look at the example first. So for the first one, we have this. So the permutations are, so you have 6 permutations here, and among them, 1, 3, 2, and 2, 3, 1 are balanced. Wait, actually, yeah, they're balanced because on the odd indices you have 1 and 2, so the sum would be 3, and then like the even would be 3, and the same for that one. For example 2, yeah, so only 1, 2, 1 is balanced. So actually, we don't actually have to form the number, I think. So like because we have we have the odd numbers and the even numbers, we just have to make sure that like they have the same sum. Let's look at this one. Okay, so this one, it cannot be balanced. Yeah. So I think this one cannot be balanced because the sum, well, if you think about it, the sum of all digits is odd. That means if you partition them into two groups, what? Yeah, if you partition them into two groups, one side will be odd, the other side will be even. So therefore, it doesn't work. So like that's the first case that can be easily dealt with. The other thing we can do. So that means like for the sum, it has to be even, right? And if it is even, we can know exactly how many numbers goes into the first group and the exact target we want. Well, the target would just be, let me write like maybe the sum. So the target would just be sum divided by 2 here, right? And let's say we have like n digits, and if n is even, then again we have n divided by 2 digits that goes there. If it is odd, it will be n plus 1 divided by 2, and then you have like n minus 1 divided by 2 here. So that means like we can set the first one to have 1 digit more than the second one. But the question still remains, because this is up to 80. So that means like we can have at most 40 digits on this side, right? Which is still quite big. So like for example, 2 to the power of 40 is, well, 2 to the power of 20 is a million, right? So 2 to the power of 40 would be the square of that, which is way too many combinations to try out. Yeah. I remember like there are definitely some algorithms that kind of does this, But yeah, I don't really remember how they work. So we have to like figure that out again. But also it has like this like 10 to the power of 9 plus 7 thing. So it I think there are two possibilities. Either like there are some sort of like DP or like some sort of DFS BFS, like probably DFS or like backtracking that does this well, or um we or we kind of like brute force, so well backtrack with some sort of heuristics to basically like cut the operations down into like somewhere around to the power of 20, and that will be quick enough. So yeah, there isn't like that many examples, I guess, that we can like look at. But hmm yeah, how do we want to go with this actually? So first of all, does it make sense to sort the numbers? um I would say it could help a bit. So like for example, like let's look at the case 1, 2, 3, 4. um yeah, actually I think backtracking definitely makes a lot of sense here. I just don't see a way to make it fast enough. So that's the issue here. But I guess like, well, we can look at like one, and then we have like a target thing here. So yeah, so like, and then we can look at two. So like the target we want to reach here is 5, right? But we also need to make sure we are only using um we are only using 2 digits. Yeah, actually, does that help at all? So the biggest we can have is like 80 choose 40, which is like this case here, right? But that's like equal to, yeah, it will be extremely large. So we definitely can't try all of them. What else can we do though? Yeah, so if this doesn't work, well, we'll have to like try the next number, and then again we have to like, so like 1 and 3 doesn't work, so we have to like try the next number again. Yeah, but this is still like a combination kind of time complexity. Yeah, 80 is actually such a strange bound that makes things very awkward. Hmm. Would something like DP work though? So like, because we have backtracking, so if the bound is smaller, backtracking would definitely work here. But obviously it doesn't work because it will be too slow. So we have to think of ways to like maybe cache the results. Like maybe that will help. So yeah, what do we want to do here though? I guess like one way we can go with it is like, I guess we can have a count of numbers on one side. So we are trying to figure out the state space if this is DP. So we'll have the count. So that'll be the the numbers we have picked, and then on the other side we will have like the the numbers available maybe. So for our base case, maybe we have something like um so let's just have some like, and then you have the sum here, right? But the sum couldn't be that big because um well, because we only have 80 digits, so like the maximum would be like 80 times 9. But I guess like in this case, in this case here, our maximum sum would just be 10. Also, like we don't want to go past our target, right? So we can actually just have 5 here, and I think it'll be fine. Like anything that goes after it, like for example, if the target, if the sum of the numbers chosen are 6 or 7, it's not helpful, right? Because we want to reach 5. So that's like another thing we can try. Yeah, I don't really have any idea how to solve this, but I guess you can just try different things. Yeah, so here, so we have a 1. So if we can only use up to 1, oh, maybe it is a 3D DP, maybe. Because like right now, what we have up here is how many numbers we can use yet. So this is like 1 to n. But then if you look at this entry here, uh, you can possibly form like a number of, yeah, actually, um, I said something wrong up here because this is like the number of numbers we can use. So for example, if n is 3, we can only use the first 3 digits. So we actually don't need the 5 here. But if we are counting the sum, uh, like the sum of the digits and like how many ways we can reach there, then it would actually be like up to 5 only, because like if the sum is like 6 or 7, it wouldn't work. So we don't actually need that. So let's look at like 1 and 1. Yeah, I guess it's extremely hard to visualize a 3D state space, but I'll just draw it out down here. Yeah. My phone is also running out of power, so my mic might die, which is, so I need to get this done quick, I guess. Yeah. So I guess like for the first case, well, if you can only use one number, then of course the count would only be 1 um at most. Yeah, actually, another thing I noticed is that if your count, yeah, so it doesn't make sense to have count 3 and 4 here as well, because if you have chosen 3 numbers already, it wouldn't be balanced, right? Because we have to clearly separate them into odd and even indices. We'll deal with the odd case later on, but like let's try to think of a solution, a general solution first, and then like we can deal with like the odd, like the edge cases. Like for example, odd is obviously not balanced, and also like for even, um, if we count this set, and then we count like 2, 3, well, they're a complement of each other, right? So for example, 1, 2, 4, 3 would work, but then like something like 2, 4, 1, 3 would also work. So like we have to account for this as well, so we don't double count. And I think like we can maybe just divide it by 2 or something, but yeah, but I think like we can deal with that later. We also have to figure out how to actually calculate the number of ways. So well, so for here we only have one way, right? So because like, well, the sum of just 1 itself would just be 1. So we have all zeros here. And then what can we do on the next one? So we can either move down or, well, I guess like for all these it will be 0, because like obviously we don't have 2 numbers available when we can only use 1. But here it will be available here. So again, let's draw out our 3D array. So for 2, what do we want to calculate? So for for these entries here, it means we can choose 1 and 2, but we can only pick we can only pick one like one of the elements. So it will be so if the sum is 1, again we have one way, and then if the sum is 2, we have one way as well. But then when we get here, I think like we should look at like because we have a new character now. So I think like what we want to look at, well, obviously this can translate to that, and then like this can also translate to that, but then we have to account for what happens, like the other possibilities we have when we add the 2 there, I guess. So yeah, so that's why like it moves from 0 to 1, because like we can just choose the 2 there. And I guess like in future cases we might have to look at like the possibilities like all the way before as well. So that would actually, like, because it will be a 3D DP, but then we have to look at like n options. So it will actually be n to the power 4. But like as I said before, it should still work. So yeah. Yeah, so for 3, well, we can look at well, because like if we add, so like, so the number of ways without choosing 2 will be added here, but also the number of ways we can use to like actually form that sum. Well, if we want to form a sum of 3 and we want to use 2, well, the remaining numbers, so the previous number, have to form 1, right? So we'll look at this entry, and we have one way there, so we'll do 2 here, and then like none of it will work down here. Wait, actually, we also need to keep count of the. We also have to keep track of the count. So actually, no, this is not the case. Because like we don't want to look at this entry here when we are adding 2. We want to look at that one. Yeah, and I know it is kind of confusing, but I think I'm getting somewhere. So if we are using 2 numbers, that means we have to look up this way, right? And then wait. So we either look at like the previous entry, which does have a 2. Which is like we either have to look at how many ways like previously that uses 2 numbers, or we have to look at like the number of ways here. And then we add our like the current number that we are dealing with. So that means we have like, yeah, so originally if we are just looking at the like the one element and count of 2, well, all of that would be 0. But when we account for this thing here, so this is when we have one element and we choose one of them. So, well, if we want to use 2, well, that means like for example for this entry, we want the previous numbers to form to form a sum of 1, and well, there is a case there, so we can just add that in. And I think like if we do this, eventually what we will get at the end, which is this entry here. This is the entry we are interested in. we can find the number of ways. So like it would be a 3D array here as well, right? And then like this obviously represents the sum. So we'll find the number of ways we can form um a sum of 5 using 2 elements. And after that, what can we do? Well, uh, yeah, actually, how many ways would it form in this case? Well, it would be yeah. So I think like for 4 here, um, so because so either we have like ways to form it before, which we will have one way, which is like by 2 and 3. So there will be one way here. So we will translate like one way here, and then when we get to here, we will look at like all the one counts, and we will look at the number of ways. Wait, do we even have to look at all of them? I don't think so, right? Because we would have counted the number, like the number of ways to form one would have been transferred here. So we only actually have to look at this entry here, I think. Yeah, I could be very wrong, but I think that's how we do it. So we look at it, and then we found out that there's one way to use one number to form the sum of 1. And yeah, when we add 4, it'll be 5. So we'll have 2 ways here now. So what does that mean? It means that we have 2 ways. So remember, like we have a partition, right? So let's say these are the odd indices, these are the even indices. So that means we have so we have 2 ways, right? I'm just checking on my phone whether it died. Should be fine because we are getting very close. Yeah, so that means like, and also because this is sorted, right? So like we have only counted like 1 4 and 2 3. But in reality, yeah, in reality, we can do something like 1 4. Well, let's say like even is like 2 and 3. We can do 1 4 and we can do 4 1, right? So that means we actually have to account for the permutations as well. So for example, for this case here, like we can rotate it to be like 1 4 and 4 1, right? So it would be like 2 factorial number of ways to do that. And then for 2 3, again, we will also have to the like 2 factorial number of ways. And this is where like the original number of indices kind of comes in, because if we look at the 1 4 case, well, for the other digits, so for 2 and 3, like because when we choose 1 and 4, that means we have 2 and 3 left on the other side. Well, it also has like 2 factorial number of ways to form, right? And like when we multiply them, we get the actual number of ways that like we can use 1 4 in the odd indices, for example. So that would be like something like this, I think. Yeah, and then you have like the 4 1 case. So these are the 4 possibilities, right? And then when you look at this case, you have 2 and 3. Yeah, actually, like before I thought you have to divide it by 2, but actually no, because like these sets are ordered. So when we put 2 3 here, it's actually different from like these cases. So you can't just like exchange the 2 sets because like they're ordered. So that means like like we just have to find the number of ways we inform. So number of ways, and then for each way, we will have like 2 factorial times 2 factorial ways to actually like form those balanced numbers. If it is an odd case, so for example, like the 1, 2, 3 example 1, so we'll only have like 1, 2 here, and then like so we'll have like 2 ways to form here, and then we'll have like 1 on the other side, which yeah, it does match up with the answer. So I think like we can check whether 1, 2, 3, 4 actually has an answer of 8, and if it does, okay, how do I get this? Okay, there we go. So let's just check like 1, 2, 3, 4. I hope that works. So let's just return like a -1. So if it is 8, that means our algorithm is more or less correct. Yeah, okay, so my idea is correct. And yeah, I guess we can start coding now. It'll be very tough to code up a 3D DP, but yeah, we can do it. We can do it. So first of all, we need mod. So we don't forget later. Oh, +7. Yeah, actually, for the number of ways we might want to like mod all of them as well, and we have a n cubed kind of time complexity, so it should be fine. Yeah, but the first thing we have to check if the sum of numbers is odd, well, we just want to return 0. Like there are no ways we can do that, and it will just save a bit of time. So now we want to run DP. Not run DP. We want to form our 3D DP, which. So I guess like for the first thing, we can have. Well, it doesn't really matter like which ways we are forming, but I guess like if we follow this here, it will just be easier to visualize. So the first one we will have the count. So actually, let's mark it down here. So we have count, we have 1 to I, and then we have sum. So for count, how many can we get up to? Well, I guess we can just do like we need the number of numbers we have. Oh wait, actually, maybe we want to turn numbers. Yeah, we can't just check this because like it's a string up here. So just do something like x4 x in num. But then we turn this into an int. So we have to like keep turning the numbers back into an int, which makes me think it would actually be better if we just turn nums into that thing. So for x in num. And then like we can just do some nums here. And I also like nums a bit better. I don't know why, but yeah, so for the count here, well, initially everything like the number of ways we'll all just set it to be 0, so we can like just add it afterwards. So 0 for. Oh wait, we actually want all of them to be 0. So for something in range, I think n divided by 2 makes sense. So if n is 4, that means like there will be 2 ways. And then we might want to do a +1 here, because like ideally we want to access like DP and then you index with 1 and 2 to indicate like how many numbers we have chosen, right? I think that would be nicer. So that's why I'll do the +1 here. If it is odd, well, for odd number, we talked about like splitting into like 2 and 1, right? Or 2 and 1, but actually like 1 and 2 also works, and it'll be better as well because we have a bit less stuff to calculate. So we have that. And then what do we want to put inside? So the next thing we want to put is like 1 to I. So we have n elements, and then again we want the +1, so like it will be easier to index. And then here we can do 0 for something in range. So that will be the sum. I guess we can like do sum up here because we need that afterwards anyways. So again, we want to divide the sum by 2 and then +1. So now we have to deal with the base cases. So what base case we have? Well, for all the DP with a 0, yeah, so if we actually, do we want to set it as 0 or 1 for those cases? Yeah, so for example, like for this case here, so it's very messy. I'll do a new page. So we have like 1, 2, 3. So that will be the 1 to I, and then we have to count. So it's like 1 and 2 here, and we are still looking at the number 1, 2, 3, 4. So for this case here, we have like the sum thing, right? Well, actually, we have a 0 there as well for the actual DP purpose. So this case we'll have to look like either across that way or above. So across, that means we have a count. We have a count of one number. So like this is the across thing. Well, it is not possible to not use any of the elements but have a count of 1, right? So all of those should be set as 0. But then when we actually go up here, how many ways can we use 0 items and a count of 0 to form a sum of 0? Well, there's actually one way. So I think that's our base case. And if we set all of them to 0, because like we are slowly like picking elements up and adding into our entries, right? If all of them are 0, well, the final answer will also be 0, and that wouldn't work. So we just want to set 0, 0, 0 to 1 basically. So DP 0, 0, 0. So we have one way to do it, and then so for count in range, so 1 all the way up to we should probably set those variables up here as well. So count, it will be n divided by 2 plus 1, and then we have the one, we can call it like 1 to I maybe. Would be n plus 1, and then we have well, I guess we'll just comment it so we know what we are dealing with there, I guess. And then we have like the sum, so that would be like s divided by 2 plus 1. So we can just comment this just to get a reference when we are a bit lost. So count, we can have this. So 1 all the way to this. So this is just following like this thing up here, which we have kind of talked about before already. So for index in range, n plus 1, well, actually, yeah, we want to go from 1 to n plus 1. And then for for sum, so we will set that as, I guess, like target. We can call it like target sum or something. So in range, again, we just want to do this. Wait, actually, how many ways can we use one element? How many ways can we use a count of 0? Like, how many ways can we use no number to form a sum of 0? I think like for all of these cases, we have to set it as 1 actually. So so this is the count. This is the amount of numbers we are allowed to use, and then this is the sum. So like my point is, if we have if we have no counts, so we're not choosing any number, we can always have one way to form a sum of 0. So that's why we have to do for I in range all the way up to n+1, we actually want to set this to be 1, if I'm not wrong. And then we can start calculating here. So for each of the target sum, what do we have to look at? We only have to look at 2 things. So again, if we go back to the graph here, we have to look at the number of existing ways without using our current number. So I guess we can set like current number up here. So that would just be nums I think. Wait, is it nums I or I-1? Yeah, I think it's I-1. Yeah, because like for here it is 1 index, but for our nums it is not 1 indexed. Yeah, so it makes sense to do I-1 to actually get the correct digit, and when we reach like I equals n, it wouldn't actually go out of bounds. So that means we are correct here. So for target sum, so dp, so we have the count, and then we have I, and then we have, I guess we have the target sum as well. So what do we want to set it to be? So either we just look at the number of ways we can form. Oh wait, so the number of ways we can already form the target sum without using our current number, or we can look at the number of ways we can form with our current number, right? So it will be I-1 as well, but then the target sum is going to be minus our current num. And if this thing is like, this thing could be smaller than 0, right? So if it is smaller than 0, we actually don't want that. So that's why we need a if case here. So I guess we can just do like, so a is equal to dp count I-1 target sum, and then b is equal to so count -1 I-1 target sum. If target sum is larger or equal to current sum, because like otherwise we'll be going into the negatives, and that wouldn't work. So else we'll just set it to be 0, and then here we can just do a plus b. So I think we will be able to form like all the number of ways. We probably want to like do a mod here as well. So now our answer is going to lie in, so the count we want would be in n divided by 2, So that's going to give us the count we want. And then, well, this will just be the last thing. So it will be using all the elements. And then the target sum, well, what do we want our target sum to be? It will be s divided by 2, right? So this stores what we want. And then so if we look back here, we have the number of ways that we can form on that side, and we need to do a permutation, right? So so how many elements we have on that side? Like we have n divided by 2. We have to do the factorial of that, and then we want to do n minus, so that will be the remaining elements on the other side. So this would be our answer, but if we just do factorial, it will be extremely large. So we actually want to like gradually modulo it. So we have our result would be equal to this thing, and then so for I in range, so we want to go from 1 all the way up to here, and then we just do so res is equal to res times I, and then we have to modulo with our number, like the very large number, and then we can have this thing here. So we want to like do that, right? So n minus that, and then plus 1. So like it will be 1 all the way up to this number here. And then like we do the modulo here, and then we just return res. So what I've done here basically simulates the calculation up here. I'm not confident it works, like it passes first try, but I think the idea is correct, but we will see. So wait, what does it say? Current sum, oh, current num, target sum, current num. Cannot access local variable. Because I because I removed the I'll just get it back by doing this. Yeah, we just don't want this part. And then of course we have to change that back. What about now? Like getting some correct. Well, this one is correct. This one is not correct though. The output is 2, but we actually only have 1 way. So why is that? Also, where did it get? Well, expected is only 1. Let's print out res. So res should be... Oh, there is a problem with my algorithm. So when we're doing the permutations, we actually also need to deal with the duplicate numbers used. So that's something that we are missing. But I think if we implement that as well, it should more or less work, I think. But that would be really annoying to do, I think. Wait, actually, is it that annoying? Because no, it's not annoying, because so if you look at like the 1, 2, 3, 4 case, right? Well, like we don't actually have to remember like all the exact permutations we have, because like we know that when we form all those like balanced numbers. So yeah, so like this is the 1-to-1 case, obviously. So when we form all those balanced numbers, well, because we are treating the first one differently to the second one, and we have to use all the digits as well. that means like if we swap these, it will still be the same number. So it would just be like the usual permutation thing we have to deal with for like all the digits. So we actually just need to add an extra step here. So we just use counter num, I think. Yeah, we want to use num here this time. So, and then I guess we can also do like for value dot values. So we are only interested in the number of duplicates it has. But we actually don't want to do division, I think. Yeah, because like when you do modulo, yeah, I'll explain why. So for example, like you have a really large number that you modulo into like let's say the modulo moduloed it into like 7 or something. Well, if we have like this case here, like because of the modulo, it will actually makes this like 3.5 or something, like when we are dividing this. So we actually need to do the inverse multiplication thing with mod, which I don't remember at all how to do, but we just figure it out. So we have a mod number here. So let's say it's like a, and then so we want to do like multiply. So let's say like the number of ways we want to divide is like C. Let's call it C. So is equal to like something modulo our mod. I guess like we can call it X or something. So yeah, actually I forgot how we deal with this, but it has something to do with like the inverse. And my phone is running out of power. I might have to just search that up. I will try a bit first before I do that. So so obviously we can swap that into like finding XC, I think. Yeah, actually, like what is 3 divided by 8 mod 5? Let's try to calculate that. So 3 divided by 8 mod 5. Like in the 5 modulo space. So we have to find the number. Yeah, we have mod 5 here. So we have to find the number such that this is correct. So mod 5. Oh, I think it has something to do with like it is the same as I actually don't remember how you deal with this case. I guess you have like this. Oh, maybe you want to find the inverse of 8, and because of how modulo works, and because of how prime number modulo works, I should say, like 8 to the power of 8 minus 1 is actually equal to 8 to the power of 4, which is equal to 8 to the power of 9. I'm not going to explain the proof here, but this is just like one thing you can do. Like when you have mod 5. So in this case, we'll have to use the power function. So import math. I think that's where the power function lives in. So we have to count here, and then so the number we want to divide. So we have results. So we want to divide results by the inverse of the fal factorial. So I think that's how factorial works. I think you do that. But then you want to do math.pow. So you want to raise that to the power of mod minus 1. So this is like from like the egg to the power of minus 1 to egg to the power of minus 1 plus whatever mod we have. So that's why we have mod minus 1 here, and then we want it to be modulo mod. So we can have that. So this is going to be our like the number we want to divide, and we can just do like now we can just multiply this actually, and then of course don't forget to mod this number. If it is 1, well, if math factorial is 1, it wouldn't actually affect anything, because like 1 to the power of anything is still 1. Yeah, so I think that should work now, I think. Oh, pow expected 2 arguments. Is it mod pow? I don't remember. I'm gonna quickly search up the Python pow function. So Python pow function with mod. I remember doing like using this in another hard question. Maybe we don't need pow at all. Maybe that's why. Yeah, it seems like it is a already built-in function. Huh. It still didn't work though. So what is this thing here? Well, actually, let's print out. Let's print fal and then this thing as well. So we should see 1 and 2. Yeah, so 2. Wait, but the factorial. Huh. Yeah, I thought this factorial would be like massive, right? Well, it should be massive. Yeah, so I think this is referring to, let's just do like items so I can see the number as well. Yeah, I'm not sure why this is not working. It should be working. So we have 2 1s, that's correct. But then the factorial of 2 should be 2. And I don't think the modulo of that would be 1 though. Even though, well, it is a massive number and we can't really see what's going on. So math.factorial value. It should say 2 there. Right, yeah, it is 2 there, but for some reason the mod minus 1 thing doesn't seem to work. That's very strange, because it definitely should be some massive numbers. Huh. Yeah, I'm a bit confused now on why this is happening. Yeah, so mod minus 1. What if I just do minus 1 here? Would that work? Well, if I do minus 1 here, this is a lot more promising. I think this is the type of number we are looking for. Yeah, I don't know why mod -1 doesn't work though. No idea why. Yeah, maybe this does the trick for us. Like, yeah, I think so. Yeah, I don't know why mod -1 don't work. Like, surely it is not because it's too big or something. Oh no. Output is 4, but expected is 8. Huh, am I miscounting somewhere? Is it because of the 0? And we can't have 0 at the beginning? Oh, that will be another issue I have to deal with. Yeah, I think it has something to do with zeros. This video is going to be an hour long. I'll put timestamps so you can just skip ahead. Yeah, so let's go back to the drawing board, I guess. Wait, but my output is smaller than the expected, which is very strange. I guess we can use this test case. And then just print out res. Wait, see, it's only one way. That shouldn't be the case because 0 and 7 works as well. So actually, yeah, it is something to do with the algorithm then. So what would this actually do? I think like when we reach 0, wait, is it? No, it's not this, because like it can be equal. So when we're looking at 2 and 0, it should look at how many ways to form a sum of 2. Is it because I didn't account for zeros up here? Is that why? Or something is wrong with accounting for 0? Like, because 0, 7 works, but I think like 2 and 5 got counted, but not 2 and 7. So I guess we can like print out more stuff. So we want to print but then if we just print it, we'll print the whole DP and figure it out from there. Yeah, so this is yeah, so this is the like only accounting for. Wait, no, this is for no numbers, I think. So like because no, this is for 0 counts. So we're not choosing any numbers here, and that looks correct. And then this is for the number 2. Is it? Wait, so we have count. No, this whole thing is for count of 0. So if you're not choosing anything, that should be correct. This is for count of 1. So like, of course, if we choose no numbers, it will be 0. For count of 1, we can have 1 here, and then for like count of 1, it will be 1 here as well, and then here, like because we are using 5 as well. So yeah, and then we are using 7 here as well. So yeah, I think for count of 1 that's correct. So for count of 2, So first one is not, it has nothing. This one also has nothing because we can't have two elements yet. And then for this case, yeah, so 20 actually does get counted. And then 205. Oh, for some reason it didn't count this case here. So this is like when we have access to 20 and 5, but then it didn't actually count yeah, it didn't actually count like for two elements. We can like look back. So for two elements, we can look back. I think it will be this case here, right? So count -1. So I guess like for all the 0 counts, we have to set it as 1 maybe? Yeah, so what's happening like in this case specifically is that we are looking at the number 5 and we're looking for a number of ways. Yeah, we're looking for a number of ways to form an array of 0 sum along with 5, right? Yes. So what would this look at? Well, for 5 here, it would be so count -1 is just 1 because we want one element. So this would be 2, I think. So you look at like the 0 to 2, 2 and 0 sort of stuff. And then here you look at 0. So that means for wait, but then we have set. So I guess like for count -1, you also want to have. So this doesn't have to be 0, I guess. Because yeah, so what it means is even if we are not allowed to pick anything, if the sum is 0, we should still have 1, maybe. I guess we can add that in, see if it works. Well, actually count doesn't have. Well, let's deal with this first. So we have I, and then we have well, actually the count here would like also be that. I guess we can just put it up here then. So for j in range, so for count, we have all the way up to this. I think j and I, we want to set it as 1. Would that work now? Yeah, so apparently we should also set those number of ways to be 1, which makes sense because otherwise we wouldn't count the like using 5 along with a 0 array, which is possible. So that should work. I think I'll still fail though. Because of the 0 cases. Wait, expected is 0. Output is 4. Well, that's very strange. I'm glad I printed out the DP thing, which we will still need to use to debug. Is it only for the 0 case that we should count that? Yeah, I think it's only for the zero case that we should count that, actually. Because yes, like my original thought is, it doesn't make sense to have well, it doesn't make sense to like have some count, but then like your zero thing, like it doesn't make sense to have like a count that's not zero. But actually if you have zero digits then it makes sense. But for this case it actually doesn't make sense because like we want to form 7, right? But we don't actually have a 7. We don't actually have a 0. So I think we also have to account for to deal with only cases that have zeros. We will deal with that outside, I guess. Do we want to deal with that outside, or do we want to deal with this here? I think we do want to deal with this here. So the number of ways to like not pick anything, so that will still be 1, which we can actually put this here. But so I think like we want to have a 0 count. Yeah, we have to deal with like the 0 edge case, which is very annoying, I think. How much power do I have left on my phone? I'm this done quickly. So if our start, so I guess like we also want to have like all the way up to 0 count, maybe. So all the way up to 0 count. And then we can do something like 0 count. So if nums I is equal to 0, then 0 count, we want to add 1 to that. And then here, so yeah, all the way up to 0 count, we want to set this as 1, because we actually don't want to set it as 1, because like let's say we have like 0 0 0 7 and more stuff, and we want to form a target sum of 7. Well, we can pick like 0 and 7, and then we can also pick this 0, and we can pick this 0. So we actually want the permutation thing again. Oh, this is getting quite messy actually. So 0. Wait, so that means we are choosing no zeros. If we're choosing no 0, it will just be that. If we're choosing 1, there would be 0 count amount of. So I guess it's like math comp. 0 count, choose J. I think. Let me just search math.comp. I think that's how you use it. Yeah, so this is number and this is count. So I think on paper this works, but then we also have like the leading 0 cases. Oh, index out of range. So if nums I is equal to 0, because we need I minus 1 when we are actually referencing the numbers. Oh, this case is wrong now. Is it the same place? So this is the count. So here we have a 5, which it should look at a count of 1 with a sum of 0. So yeah, actually this thing should be set. to 1, I think, because it will be looking at that element. Well, if it does actually change this, it should deal with that case. Yeah, I'm not sure where the problem is. So when we are looking at oh yeah, also this would be messing things up because like, so we want to put dp 0 0 0 equals 1 outside, I think. What else do we want to do to fix this problem? So we will have increased the 0 count when we reach 2 here. So that means for 0 count, oh, I guess like it needs to be +1 because it is exclusive, and we can that should work now. Yeah, I just forgot to add that in. We also have the leading 0 case, which I'm not sure. Oh, output limit exceeded. It's probably this. Wait, number. I feel like we are getting close, but my phone is also dying. It says index out of range when it is all zeros. Huh. Yeah, we're definitely getting really close. We only have like a few cases left. Can we just brute force the last case actually? Like when they're all zeros. Guess technically we can. Let's just try to like, I want to see what kind of answer they expect for all zeros. So they expect, oh, one way only. Oh yeah, because of the modulo, of course. So I guess like if s is 0, we just want to return 1. Maybe we can do that. That can silence the 0 case. I'm not sure why it is doing that here. But yeah, it's probably like just, or maybe like, I know why. And my phone is 1%. So the problem is for math comp, if we have no zeros, so I think like, is it because math comp 0 0 doesn't work? Yeah, I'm actually not sure why it's doing that, but it worked, which is amazing, I guess. Oh, result not supported. Yeah, but I guess it has something to do with like either this case here or like we are, maybe we are like some, oh, it could be like for count. Wait, it could be for sum, like for the target something, because it is 0, like when we do like divided by 2 and +1, it just becomes a bit janky. But yeah, this, well, again, I saw modulo. It has to be DP. Well, not has to be, but is most likely DP. And then yeah, and then also like my first idea is backtracking, right? Which it does work. Like backtracking definitely works. But it's just too slow. And if backtracking is too slow, the first thing you should think of is DP, because DP usually uses like caching to turn exponential algorithms into polynomial algorithms. So I guess that's how I got there. And then in terms of the like how I thought of the 3D DP, I just think of like the different states we have. So like the first one, it like because for DP you want to exhaust every single possibility, right? So when we look at the ith element, and we want to like form some sum, and like we also are interested in the count, right? So so I guess like maybe I'll explain each of them. So count definitely makes sense to be in there because like for our number of ways, we have to take account of the number of numbers in the set. For 1 to I, it makes sense to like look at each number, and like because if you look at each number, so like for example like 1, 2, and 3, if you want to form, let's say like the number of ways to like form a target 5, it makes sense to like either use this number or not use this number. So if we can form target 5 before, we want to add those ways, and then we want to find like the number of ways we can like use 3 as well. But then that means like for the previous stuff, we want a sum of 2 and count of 1. So that's also where sum comes from. So, and then, well, I guess like the first modular thing, you just have to know like there is no getting around for this. And then for the factorial thing is also like a math thing, but yeah, I guess that's how I got the answer. But I have to go now because my phone is about to die. So I'll end the video here. I'll put timestamps below as well, so you can skip ahead. So yeah, thank you for watching, and I'll see you tomorrow. Bye.